Okay, this is our first lesson on Unit 3, and this is going to be representing probability distributions. Really what we're going to find out is that we're going to be making probability distributions kind of like we did with mathematical functions in grade 11. So one of the big things that we're going to be talking about in this unit, though, is what do you expect to happen? And we've started this conversation before with the law of large numbers, and we're going to continue this conversation today. It's just some Canadian content for Leonard Cohen, just a quote about expectation. Um, so really, to calculate what we expect to happen, we need to model probability situations. And in this lesson, we're going to learn about modeling and calculating expected values so you can determine what you expect to happen in a given situation. Here's a warm-up question. How much do you expect to win every time you spin this spinner? I just want you to think of a number, but every time you every time you spin this spinner, how much do you expect to win? Um, so the question's not asking like, what do you want to win? The question's like, realistically, what do you expect to win? And what we're actually asking is, what on average do you expect to win if you spin this spinner over and over again? So the big idea doesn't change. Learning goal is learning about basic probability distributions in order to model probabilities for all the possible outcomes. We're going to learn how to calculate expected value, how to display probabilities in a table and a bar graph, and communicating the difference. And that's actually the relationship between expected value and the mean. So the question of expectation is not so much like I expect to get lucky or I expect to win. I got to be confident. From the law of large numbers, we know that we can calculate what precisely we expect to happen. So the question is, what do we expect to happen? So now if you have something like this, now we can actually find the average. And so we're not actually going to find the average by adding up these 4 and dividing by 4. That's not going to be the correct average. We need a way to give weight to each one of these so that we can actually calculate a weighted average. And that's actually what our expected value is going to be. That's what our average is going to be. So you need a little more information. So from this information, you could pause the video and try to actually calculate the expected value. What do you expect to happen? How do you calculate that average? So some definitions here. A discrete probability distribution is something that describes all the possibilities of a probability scenario. So it's every different value. So you're going to remember that like in grade 11, we use graphs, table values, formulas, so that we can find a y value for every x value you input. And that's what we're going to do today. So a couple definitions you're going to come back to is this definition of a discrete variable. So discrete numbers are actually obtained by counting. There's only certain inputs that they could take. And the common misconception is that they can only involve whole numbers. That's not quite true. It's just that you can input every possible value. Continuous functions are things that are obtained by measuring. So it's actually not possible to input every specific, like it's not actually possible to write down every specific value. You need a function, an equation that will model it. The nice thing about probability distributions is because there are only certain inputs, you can actually model them with a table of values and a bar graph. And we don't actually need an equation, although we'll have a couple distributions we have equations for. Here's a very simple example. It's a uniform distribution, just rolling one die. And if you roll one die, these are the x values that you could get. So these are the possible outcomes, and then these are the y values, and so they're the probability. You notice that this column actually adds up to 100%, and that's always true in a discrete probability distribution. You can also write them in a bar graph, and so this is again rolling a die. And so you can see the percentages for each x value. You can see the y value, which is the percentage chance. In previous units, we called set A or set S the set of all total outcomes. We use these letters A and S. But when we discuss probability distributions, we're going to talk about X as the set of all possible outcomes. It just redefines us so that we can kind of be consistent with mathematics, where we're talking about an input variable and independent variable. And we actually use like uppercase and lower cases in discrete random variables. So when we talk about the general idea, we use the uppercase x. So all the x values are 1 to 6, and then the lowercase numbers are the specific values. So the big X is a set. That's why it's like the big X and not little x. But little x is actually specific numeric values. It allows you to speak in general terms and specific terms just by changing the case. Expected value is a general idea, so we actually use uppercase, and you're going to notice that in the formulas. And this may become confusing, but you might come to appreciate this when we use it. You might not even have to worry about it too much. Because like we can actually say the p, because it's a diroll, it's a uniform distribution. It actually has a formula. It's always the same. It's just 1/6. So we can say p of big X, because in general it's always 1/6. Here's the expected value formula. You notice how it's e of big X. It's actually this. So this is, if you tried that spinner question, this is the probability. This is how you would actually calculate it. You take all the probabilities, which are out of 360, and multiply it by every x value, every dollar value. And then what this is, it's just a symbol for add them all up. So you sum up all of the x times p of x values, and those are specific values that you would add up. And so as an example, we can figure out the probabilities from their probability out of 360. We could show that in a bar graph, and that's just from a spreadsheet. You can copy and paste. We'll do a spreadsheet example of a bar graph later, because you'll need it for the games fair. And then to do the sum of xp of x, like a nice way, if you already have the chart, the table of values in the x and y column, we actually just make another column called xp of x, and we just multiply the numbers and add them all up, and we get 3.93. And so on average, you're going to expect to win $3.93 every time. Each of these individual numbers do mean something. They're just the contribution of each section. So on average, the $20 section will give you $1.94 every time. You're not going to roll 20 all the time, but like that's what it balances out to. And then when you add them all up, that's $3.93. So if all these sections were 0, and there was only a $20 section, your expected value would be $1.94. But because there's 4 different prizes, you can add them all up. Plinko, this is a fun video you can watch, but Plinko is another example of a what we call a non-uniform distribution. So Plinko, if you think about it, so this is the question, like how do you get the probability of any of these slots? And if you look at it, it's actually Pascal's triangle. Like you just ask the question, like how do you get to each one of these numbers? And so if you had to drop it down the middle slot, that's a big if, but if you had to drop it down the middle slot, there's like 84 ways to get to here. There's 924 ways to get here. And so that's basically how you find, just like we did combinations, the pathways. Pascal's triangle tells us the number of pathways to something. And so we can actually create like a table of values for each slot. And so we just take the total number of ways to get there. So 0 would be 792 plus 792 divided by the 4,000 total. So 39.6% of the pathways that get to the bottom, they all do get to the 0. And then 24.7%, 33.5%, and you can see that these add up to 100 again. The expected value, if you multiply straight across, you get $1.05 when you add them all up. This is kind of neat because like we're getting ready to like look at our games fair later on in the unit, and so this is an example of a board that you might want to change these outcomes. So if you look at the game itself, it's not very exciting, and so but if we just have starting points for the outcomes, now we can change these numbers, and our expected value will change so that the game's a lot more exciting. So if you created a grand prize, what would that drive the expected value up so that you can now charge money for it? So now what we're going to do is demonstrate that expected value is an average, and by average we think of adding them all up, dividing by the total. Um, and so if you think about 4,000 different coins dropping in the middle slot, we can actually say like 4,000 is a really nice number because then we could say, and that's what distribution really means, how each of the trials are going to be distributed. We actually expect in 4,000 trials, 1,584 of them to be 0, 988 of them to be 1, and 1,340 of them to be 2. And so we can actually like add up those numbers, and add up those numbers as many times as like we expect to happen, divide by that total 4,000, and you can multiply instead of, like, you're not going to sit there and add that many times. Um, but this is actually how you calculate an expected value. Um, and it gives you 4,021 over 4,000, which is $1.05. Um, I like this process too. It's the exact same thing we just did with the chart, but it just shows the multiplication in a different order so that you can really emphasize the idea of average. I think it's easy to kind of get caught up in the chart and say that, oh, we just make this third column and that's going to be our expected value. But you maybe don't really understand what that means. And so I think by doing it this way, and so is basically proving, and so it's mathematical proof that that expected value, that third column, is the average. And so that's kind of neat to play around with. You don't have to create an example necessarily that's this confusing, it's this big, but this is a good one because it really clearly shows how to figure out what to choose for that nice number. It's just the n of s, the total number of ways, and how the distribution works. Again, we can always display things in a bar graph so you can see the unlikelihood of 4 and the kind of like likelihood of 0, 1, and 2. When you're creating a game, what you're asked to do is like actually not create a fair game. A fair game is where the expected value is 0, so the cost of the game is equal to the amount that you expect to win from, or the player expects to win. But really, the nice part about this unit is that we can create these games and see how like almost like get on the inside, where we're actually building these gambling games, these scratch tickets, so that you can see how gambling works and begin to understand it, and begin to understand just how the complex games can be built. So just in practice, I'd actually encourage you to do this, like create your own simple games fair game. Use non-uniform distribute, and like don't just say probability is a quarter, a quarter, a quarter, a quarter. And then share it with somebody. Ask them if they would play it. Like, okay, here's what I'm charging for the game. Here's your prizes. There's only 4 outcomes here. Ask them if they would play it. And then calculate your expected value. And I think you would have done that to determine the cost of the game. But calculate it with the average, so that suitable number of trials using n of s. Here's some more practice. Just thinking about some questions.